All right, so in the last video, we did a few examples of finding derivatives using the chain rule. And we talked about some of those generalized rules that come from the chain rule, which are still shown here. I want to do a few more examples of more complicated derivatives where the chain rule and these kind of general rules are just one step in the process. So let's start with this one. For part A, I'm looking at a product of two functions, which means I would first need to use the product rule. So for this one, I'm going to break it down the way I normally would with the product rule. I'm going to think of this first function here as u, and this second function here as v. And so the derivative of this would be u times v prime plus v times u prime. That's the product rule. But in order to pull that off, I would need to know what u prime and v prime both are. So starting with u prime, notice that what we have here is a composite function. There's 6x squared plus 5 sitting inside a set of parentheses, and that's raised to a power. Rather than think through the chain rule that I did, the way that we were in the previous example, we have this generalized power rule right here, which I'm going to use, and that's just a consequence of the chain rule. So what it says is that I take the power and I treat it like I would the power rule normally. I take that power down, subtract 1 from the exponent, and then that whole new expression gets multiplied by the derivative of whatever function was on the inside there. So u prime, I take that 9, bring it down, leave the inside alone, so 6x squared plus 5, subtract 1 from the exponent, but then I multiply this by the derivative of the function that's on the inside. The function that's on the inside, its derivative would be 12x. Remember, that constant becomes a 0 when I take its derivative. So I multiply this by 12x. Okay? V prime, we need that as well. I use the generalized power rule on that guy as well. So v prime, I'll bring the 15 down. 4x minus 9 stays put. Subtract 1 from the exponent, it becomes a 14. And then that gets multiplied by the derivative of the inside. The derivative of that function in the inside is just 4. So I have times 4 here. Okay, now I can simplify these further. I can multiply this 12x to this 9 right here, which I will do. That would make 108x. And then this 4 can be multiplied to that 15 to make a 60 there. We'll do that once we actually put together our product rule. So the product rule, since y is equal to u times v, y prime would be equal to u v prime plus v u prime. And I have all of the ingredients here. So u is 6x squared plus 5 times 9, to the power of 9. V prime is this. So I'm going to go one additional step and take the 15 and the 4 and multiply those together. I'm going to write that as a 60 right there. V prime has that 60 times 4x minus 9 to the 14th power. Okay, that takes care of this first part. V u prime. So v, we're adding v u prime. V is just 4x minus 9 to the 15th power. U prime, which we worked out here, is this. Let's simplify it a little bit by multiplying the 12x to the 9 to make 108x times 6x squared plus 5 to, what were we doing, u prime, to the 8th power. Now I could just leave this as is and, kind of call it a day from there. Or I could simplify this by factoring some things out, which we may actually want to do. So for example, if you notice, I have like kind of two big terms here, one right there, one right there. And amongst those terms, I have 6x squared plus 5 to a power showing up in both of them. I'll take the smallest power, which is 8, and pull that out. That would be 6x squared plus 5 to the 8th power. That'll come out. And then I also have this 4x minus 9 to the 14th power, and then 4x minus 9 to the 15th power. That's kind of a common factor of 4x minus 9 to the 14th power, which can be pulled out. 4x minus 9 to the 14th power. We're going to factor that out as well. Then I have this 60 here, and 60 and 108. Those both have a common factor that can be pulled out as well. I can pull a 12 out of each of those. So for example, if I factor a 12 out of 60, that's 5 times 12. 12 out of 108, remember that came from 9 times 12. So that 12 can come out as well. And if we look at what's left from each of these terms, I have a 6x squared plus 5 that's left because I only pulled 8 of those out and there was 9 of them there originally. So I'm going to have a 6x squared plus 5. From the 60, I factored out a 12. That will leave a 5 behind. And then the 4x minus 9 to the 14th power, I pulled out completely. So that's what I'm left with. Here, 4x minus 9 to the 15th power, I pulled all but one of those out when I factored. So that leaves me with 4x minus 9 just by itself. 108, I pulled out a 12. It leaves a 9 behind. This x didn't go anywhere, so there's a 9x there. But this 6x squared plus 5 to the 8th power, that whole thing factored out. Okay, so that's out here now. Finally, with what's left in here, I can simplify things down. So I have 12, 6x squared plus 5 to the 8th power, 4x minus 9 to the 14th power. And then here, if I distribute this 5 in, I'm going to get a 30x squared from here, and then I'll get another x squared term from right here. 4x times this 9x, once it distributes in, will be 36x squared. So I have 30x squared plus 36x squared. That makes 66x squared. And then when this 9x distributes into this negative 9, that'll produce a minus 81x. And this 5 times that 5, once it's distributed, gives me a plus 25. Okay? Now, I could keep going and try to simplify this to see if it factors. I'm not going to worry about that. This is as far as I really care to take this one. Technically, we found the derivative all the way back here. So these extra steps of simplifying are just sort of algebraic steps that we oftentimes do. The reason I wanted to work through it here is because later on, when we're applying the derivative to various different things in chapter 3, a lot of the time, I think I mentioned this in a previous video, a lot of the time finding the derivative is just a step in the process. And what we're doing a lot of in chapter 3 is we are taking that derivative, we're setting it equal to 0 and then solving, because that has a special significance for some of the stuff we do in chapter 3. When I have the equation in this form, or up here, when the derivative, sorry, not equation, when I have the derivative in this form, it's difficult to solve this the way that it's written if it's set equal to 0. But if I set this equal to 0, I have it written as a product of 4 different expressions. And we could use the zero product property from algebra to set each individual one of these equal to 0 and then solve that. So again, my whole point here is that normally, if all we're asked to do is find the derivative, I could technically leave it this way and be correct. But later on down the road, when we use these derivatives for different applications, we're going to find it much more helpful to have it in this form. Okay, that's enough on part A. Let's try the next one, part B. So looking up here, part B is log base 2 of x squared over x cubed minus 2x plus 7. Okay, so on the outside, I have a logarithm, which means I want to use the generalized logarithm base b rule. It's base 2 in this case. This rule says that my derivative will be of the form g prime of x over g of x times the natural log of b, where the g of x in this case is whatever's inside that logarithm. So this thing right here is g of x. If I want to write this using the notation of the generalized logarithm rule, this is what I would be writing. Okay. I also need G prime. That was one of the things that showed up. G prime would require the quotient rule. So the quotient rule says take the denominator, multiply by the derivative of the numerator. So the derivative of the numerator is 2x. My denominator is this, x cubed minus 2x plus 7. Then I subtract from that the numerator times the derivative of the denominator. So that's x squared times the derivative of this would be 3x squared minus 2. This whole thing goes over the square of my denominator. So x cubed minus 2x plus 7 squared. Okay, I am going to simplify the numerator by multiplying some stuff out, combining like terms. I see here that I'm going to multiply 2x times x cubed, which is 2x to the fourth. I also see that I'll get another x to the fourth term once this x squared is distributed here. That would give me a negative 3x to the fourth. So 2x to the fourth minus 3x to the fourth is negative x to the fourth. Okay? As I look through this, distributing these guys into the sets of parentheses that they're next to, nothing is going to give me an x cubed term. So let's look for x squared terms. I can see right here, 2x times negative 2x is negative 4x squared. And then here, negative x squared times negative 2 would be positive 2x squared. So negative 4x squared plus 2x squared would be minus 2x squared. And then let's see, will I get any x terms? Yes, 2x times 7 would be plus 14x, and that's the only x term in the whole thing. And that takes care of all of it. So we have x cubed minus 2x plus 7 there. Okay, so basically what I have done is I've computed the ingredients. There's the whole thing. And again, remember, we're using this logarithm rule with this function acting as the g of x there. So I'm going to piece together everything that I just found into my derivative. Y prime is equal to g prime. I know it's off the screen here, but g prime of x was in my numerator. It was this, negative x to the fourth minus 2x squared plus 14x over this guy. So, and this was supposed to be squared here. X cubed minus 2x plus 7 squared. And we are dividing that by the natural log of b. And remember, b in this case is the base of our logarithm, which was 2 in this example. So natural log of 2 times g of x, which we have right here. So that's going to look like x squared over x cubed minus 2x plus 7. Okay, we could do a little bit of simplifying here because this denominator and this denominator are pretty close to matching. I can cancel one of those with this whole thing right here. And then the other one can get bumped down into the denominator of the larger rational expression. So I can write this as negative x to the fourth minus 2x squared plus 14x over natural log of 2 times that x squared times this one additional factor of that x cubed minus 2x plus 7. So that's natural log of 2, x squared, x cubed minus 2x plus 7. Just like that, okay? And again, it would not have been wrong if I had left it in this form. But again, because we want to use these derivatives in some applications later, it's beneficial to us to have this thing in a simplified form. So this is much more simplified than the way that we wrote it here. Okay, let's take a look at one more. See, I have the natural log of the square root of 7x plus 13 all over e to the negative 5x squared. Now, this guy looks pretty similar to what we had over here, right? Because this log base 2 had log base 2 of a quotient here. So I could approach this one in essentially the same way. Because it's a natural log, we have that one has its own rule, which is actually just a special case of this rule, because when you take the natural log of e, you just get 1 and it's not written there. But I wanted to approach this one in a slightly different way, just as an alternative, because if we know our logarithm properties, you can make this simpler. You can make this a lot easier. So let's I don't know if I have enough room down here to do it. I'm going to do this on a separate sheet right here. Okay, so g of x, this is part C, g of x is a natural log of a big complicated expression. We talked about in the first week of the class how to expand logarithms. I actually could have done this with this example too, but I wanted to do this with the most direct approach first so you can see an alternative approach here. The natural log, or let me write it as g of x. G of x is equal to the natural log of the square root of 7x plus 13 all over e to the negative 5x squared. This can be written the same way, or this can also be written like this. Square root of 7x plus 13 minus the natural log of e to the negative 5x squared. Okay, this is from one of our logarithm properties. We know that if you're taking the logarithm of a quotient of two things, you can split it up into a difference of logarithms like this. Numerator goes here, denominator goes here. Now, in addition to that, this square root can be written as 7x plus 13 to the 1/2 power, right? And this over here, I'm taking the natural log of e to some power. Remember, the natural log and the exponential function e to the x, those are inverses of each other. These cancel. And what I'm left with is minus, from that minus right there, negative 5x squared. Okay? From here, I have another logarithm property that's really helpful. And when you take the logarithm, it doesn't have to even just be a natural log, any logarithm of something to a power. You can take that power out to the front of that logarithm. We talked about that property in the first week of class. So this becomes 1/2 times the natural log of 7x plus 13. And then this negative and that negative cancel, become a plus 5x squared. All right, in this form, this logarithm is way easier to evaluate because I don't need the quotient rule. And even if I did use the quotient rule here, part of that quotient rule would require me to then also use another application of the chain rule to deal with this radical here. I'm dodging all of that because if I take the derivative now, g prime of x, it's 1/2 times, here I use the general rule for the natural log function, which says that this is equal to the derivative of the inside function, which is just 7. 7x plus 13, its derivative is just 7, over that function itself, 7x plus 13. Super simple. Then here I use the power rule, plus 10x. That's it. I could multiply this 2 in here. I'm just going to leave it in this form, though. By doing it this way, this problem is much simpler. There is an optional section in this, or an optional little subtopic within section 2.5 that talks about something called logarithmic differentiation, which uses this kind of technique. Basically, what you're doing is you're taking a function that's really, really complicated that you want to take derivatives of. If it says y equals some complicated function, then you take a natural log of both sides and use the natural log to decompose that complicated function down into easier to manage chunks like this. So we're not, that's an optional section. We have enough to cover here. We're not going to go over that, but this is something to keep in mind. Logarithms can be broken down into much easier to manage pieces. So you don't have to do you know, a complicated chain rule with a quotient rule with another chain rule. It can get really ugly if you approach it that way. You even saw that here. Part B wasn't too bad, but it's kind of messy. So anyways, I'm going to stop this video here. We'll look at some more examples in the next video.